Hello everyone to this edition of the Radiation Heat Transfer Learning Journal. So in the last video we were just talking about deriving some equations to develop heat flux in terms of temperature, right, for a gray surface. Now as you might have already noticed, it's still pretty challenging to get an explicit relation for heat flux, right? As we've seen here over here in this paragraph, say for a gray enclosure with an integral equation that must be solved, where the dependent variable QR appears inside the integral, it makes it very difficult to obtain a solution. Okay, so they do some more mathematical magic to do it, and at the end of the day, you just end up with a pretty complicated equation that you probably need computers to solve with. So what can we do to simplify things? Well, in the past, we have this thing called the electrical network analogy, which helps to give us a sort of a visual as to what's going on. So what is this electrical network analogy? So let me just refresh our memory. Okay, so this one is called electrical network analogy. So this is 5.4 of Modest of Michael F. Modest textbook. Alright, so this is pretty good, important for us to have a physical handle of what's going on. So as with all analogies, let's just talk about electrical networks for one. So let's say you have a potential V1, or let's do a very simple circuit, right? You have a battery and then a resistor, and over here the potential is V0 or V1, and the potential here is V2. Alright, so the current, which we will just conveniently name Q, is equals to V2 minus V1 over some sort of resistance. Now whenever we see this sort of pattern where we can sort of identify some kind of flow and two quantities that represent potentials and some sort of resistance, we can sort of do this kind of a method. Now, where have we seen this kind of thing going on before? Now, if we take a look at this, we see some kind of heat flux per unit area. Of course, if you want to multiply by area, okay, then we'll have the heat flow, Q net times A equals to epsilon A, so whatever area that is. So if we were to say this is like the current, so to speak, okay, I'm going to do this like that, do it like that, and I'll just invert this, okay. So this, okay. So if we were to rearrange the equation like this, we will sort of see some sort of a similarity, right? If let's say the current was Q net A, the potential difference equals to whatever is this on top, and then the resistance will be equals to whatever this thing is at the bottom. So this is where our electrical network analogy comes about. So let's take a look at what 5.4 has to say. Alright, so let's take a look at 5.41 first. This is the generic kind of equation first. Let's explain what it means. So it's nothing too different from what has been emphasized on before. Alright, so I'm going to delete this, and let's see, there's the Q coming from surface I, So let's say we have an enclosure. All right, we have a collection of surfaces of arbitrary shape. So 1, 2, 3. Okay, let's have a external radiation. 3, 4, 5. All right, so we have surface I. All right, so the net heat emerging from surface I is, what is it equal to? It is the radiosity of I. So this is a heat flux. Yeah, we have divided by area throughout, or we can simply do this. QIAI equals to, all right, so the net heat coming out is JI AI. All right, and then what is the net heat coming in? So you have to subtract H naught AI. Okay, so whatever H naught that is impinging on I, this is the external radiation that comes on I, on surface I, which is over here. What is the radiation coming there? That's H naught I, and you just multiply by AI. And of course, you will also have a summation of, okay, so we'll have a summation of heat coming from here to here, from each of these surfaces, right? So what is the heat coming from, let's say, surface 1 to surface I? So from surface 1 to surface I, the total heat is, okay, A. In this case, it is the first surface, so it's A1, right, into J1. So this is the total heat coming off that, and you need to do a view factor from 1 to 2, right? So if we do the same for not just surface 1, but 2, 3, 4, 5, blah, 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 we will end up with this. So instead of A1, we denote it AJ because it is the surface that isn't I. So this is surface I. Whatever surface that is not I, it will be called surface J. So AJ into the radiosity of JJ, and the view factor is FJ going to I. So this is going from J equals to 1 to J equals to N, right? So this is just summing up all the contributions from this surfaces. You can have n surfaces, it doesn't have to just be 5. Okay, so what is this saying? It is saying the total heat coming from, let's say, surface J to I, or surface 1, 2, 3, 4, 5, whatever to I, it is this much. This is the total heat coming off the surface, and this is the fraction of heat that goes from this surface J to surface I, right? Okay, so now we just divide everything by AI. Divide everything by AI, so you have Ji minus Hi naught minus summation from J equals to 1 to N. So we'll have Jj Fj to I Aj over Ai. And lo and behold, we can use this reciprocity relation. All right. So I'll just copy this over to give us a clearer picture of where all these things come from. It's not pulled out of thin air, but it's it's not pulled out of thin air, but it has a grounding in the representation we have. It has grounding, physical meaning. That's what I mean. There's physical meaning. Okay, so we can use reciprocity relation to say F I to J equals to, okay, F J to I A J over AI. So if we were to substitute this in, we will just get QI equals to JI minus H underscore IO Okay, so or hi naught, and that will be subtract. No, then you will have to subtract the sum from j equal 1 to n of j f j to I, or I to j, yes, I to j. So this is where this equation has come from. So qi equals to ji minus the sum of fjj, fi to j to jj, this summation term here, minus h naught I. So that's the contribution from the externals. That's all this equation is telling us. Okay. So let's put this equation to use. I've just explained equation 5.41. Let's put that to use, and we consider the simplest case of two infinite parallel plates without radiation, right? So let's consider two parallel infinite plates without radiation, without external radiation. So I'm just gonna do gray plate 1, which is on top, gray plate 2 is at the bottom. So let's go A1, and this is A2. And on top you'll have some radiosity J1. This is J2. Okay, so what is the heat transfer between them? Okay, let's do this slowly. So we know that let's say Q1, so that is equal to J1 minus 0, because there is no external radiation. And then we need to include the heat transfer from this surface here, which is J2. So J2 F, okay, F what? 2 to 1. Now, conveniently, because these plates only see each other, so everything emitted by oh, it's not 2 to 1, it's 1 to 2. Okay, so everything emitted by plate A1 is going to be received by plate A2. So in fact, the view factor here is just 1. So we have Q1 equals to J1 minus J2. Okay, so this is what we have in this case. So where is this current again? Okay, where's the current again? The current is basically this Q1 to A, and this is the so-called potential difference. So we can see that in this case, for parallel plate, the potential difference will have a resistance, will be meeting a resistance of 1, because okay, J1 over J2 divided by 1 equals to Q1. So this is like the voltage. The radiosity is like the voltage, this is like the current, and this is like the resistance. Let's check whether it is really the same in this textbook. Okay, so yep. So you can see that the radiosity, the difference in radiosity does play a difference. Okay, I think I forgot to add the area in. Of course, I did not add the area in, but if we did add the area in, it will be like infinite kind of a flow between the surfaces. So actually I should be adding the area in. So what we have is a heat flow per unit area, so it's like a current per unit area kind of a thing. So okay, so this becomes the resistance, which is 1 over A, or in this case, yeah, the view factor will come into play as well. Yeah, but anyway, so if we want to compare what we were doing to the textbook, it looks like a slightly different kind of a thing. Now, why am I saying that? Now look at the equation 5.41 we have here. Now, if this were rearranged into this form, 5.42, it is rearranged into this form, it will be much easier to see why this thing looks like a resistance model. Now, okay. So anyway, we just compare what we have here. Q1A equals to J1 minus J2 over 1 over A. Alright, so that's the first difference. So I just multiplied by that. But apparently, they have this J1 minus J2 for 1 over 1 minus 1 over A1 into F1 to 2, which is the view factor, right? So we notice the two differences between this, and probably going to ask why doesn't the view factor here also pop up here? So we can see that because earlier, I think in the textbook, they rearranged their equation as such because, okay, yeah, it's more generalizable. And okay, how did they get this equation? So let's go back to our diagram. So instead of two surfaces, there are n surfaces now. Okay, you have this case of n surfaces, or you have multi-surface kind of a thing, and then we see that okay, there is this amount of radiosity being coming out of the surface I. Alright, so there's this amount of radiosity coming from the surface I. So there's Ji, or let's just label this Ji. That's the radiosity coming off the thing. So where does this radiosity go? The radiosity is going to go into all the other surfaces. So if we were to say sum up something like this, okay, including this open enclosure here, we can just assume everything is lost there. But how much of this radiosity from this surface I is going to go to, let's say, surface 1? So that is the view factor again from, okay, let's say I going to J. So this is surface J because this is not I. Alright, so and that will be going into the radiosity of I into the area of I. Alright, so that is how we that's how we do this. So we'll not just do it for one surface, we'll do it for every other surface. So J going from I to N. Alright, so the heat transfer from here to here is one part, heat transfer from here to here is the other part, heat transfer from here to this opening is another. 4, 5, 6. So there are so many other surfaces, so we can take this into account. Alright, that's the first thing. So if we were to replace it by this, okay, I'll need to add a disclaimer. This should be AI, yeah, JIAI. Alright, so JIAI, that will be, yeah, that's better. So this is wrong. I'll need to put JIAI. JIAI equals to sum from J equals to 1 to n, f I to j, it's not I equals j, I to j, ji, ai. And of course that just means ji equals to this much. Alright, so I'm not going to elaborate more on this. Basically, I can just substitute this in here. And now you see the similarities. We can start grouping all of this together. We can group these two summations together because they are the same sign. It's j, j. And that's how we get our equation. And then if we were to substitute this equation into this formula here for this case, we would see that okay, q1a equals to j1 minus j2 into f1 to 2. All right, and hi0 is just 0. So once again, if we were to put in the array here, it will be like such, and we can see that the resistance, okay, okay, so this is the voltage, so to speak, and the current, so to speak, or the resistance, so to speak, will be this. Okay, this is the resistance in this network analogy. So I'm going to stop here for this perhaps part 1 of network analogy. I'm going to continue the explanation as to why this is still kind of valid and how we actually come to the same conclusion as over here. Alright, so see you in the next video. Thanks for watching.